plastic holding tank uses two bulb floats to control two pumps via separate 240 volts 20 amps circuits. A frayed SJAW cord caused one wire to contact the water, resulting in an electrical tingling when touching a brass valve. The copper piping in the residence is grounded per code. The SJAW cords do not have grounds. Even if the SJAW cords had grounds, they would be sealed in the bulb floats. Here are troubleshooting steps to help resolve this. Firstly, check the circuit breaker. Ensure that the 2-pole 20 amp circuit breaker is in the off position. Secondly, inspect the SJAW cords thoroughly for any damage or fraying. Replace any damaged cords. Thirdly, check the bulb floats. Remove the bulb floats and inspect them for any damage or water leakage. Ensure that the wires are properly insulated inside the bulb floats. Replace any damaged bulb floats. Fourthly, inspect the pressure pump for any signs of grounding issues. Ensure that the pump is properly grounded to the electrical panel. Fifthly, test the circuit. Once all potential issues have been addressed, reassemble the system and test the circuit. Use a voltmeter to ensure that there is no voltage present between the water and the grounded brass valve. Also, consider using GFCI, ground fault circuit interrupter, outlets for the pumps to provide additional safety protection. Install a proper ground rod for the holding tank if one is not already present. Ensure that all electrical connections are made securely and in accordance with local electrical codes. The electrical tingling experienced is most likely due to a frayed SJAW cord allowing a live wire to contact the water. By following these troubleshooting steps, you can safely resolve the issue and restore proper grounding and electrical safety. It's critical to understand the potential hazards of electricity and water. Even a small current can be dangerous, and the fact that you felt a tingle indicates a serious fault. Let's delve deeper into each of the troubleshooting steps to provide a more comprehensive understanding. Examining the circuit breaker is paramount. A properly functioning circuit breaker should trip, meaning switch off automatically when it detects an overcurrent or a ground fault. The fact that the 20 amps breaker did not trip when the wire contacted the water suggests it may be faulty or that the current leakage was below the tripping threshold but still dangerous. It is imperative to test the breaker itself. Breakers can fail over time, losing their ability to trip at the rated current. A breaker tester can confirm its functionality. If the breaker is found to be faulty, replace it immediately with a new 2-pole 20 amps breaker that meets the required safety standards. Next is inspecting the SJAW cords. SJAW cords are designed for hard usage and outdoor applications, but they are still susceptible to damage, especially in wet environments. Carefully examine the entire length of the cords for any signs of cuts, abrasions, or cracks in the insulation. Pay close attention to areas where the cord enters the bulb, floats, or connects to the pump. Water can wick into the cord through even the smallest breach in the insulation, leading to corrosion and electrical leakage. If any damage is found, replace the entire cord. Do not attempt to repair it with electrical tape, as this is only a temporary fix and does not restore the cord's original insulation properties. Consider replacing the SJAW cords with submersible pump cables that are specifically designed for continuous immersion in water. Checking the bulb floats is important. Bulb floats are a common point of failure in these systems. Over time, the plastic can become brittle and crack, allowing water to enter the float. Water inside the float can create a conductive path between the wires and the water in the tank, leading to electrical leakage. To inspect the floats, first disconnect the power. Then carefully remove each float from the tank and thoroughly examine if there are any signs of damage, such as cracks, holes, or discoloration. Shake the float to check for the presence of water inside. If water is present, replace the float immediately. Even if no visible damage is apparent, it is good practice to replace the floats periodically as a preventative measure. Ensure that the replacement floats are rated for submersible use and are compatible with the voltage and current requirements of the pumps. Make sure the wire connections inside the bulb floats are secure and properly insulated. Use heat shrink tubing to seal the connections and prevent moisture from entering. Inspecting the pressure pump itself is crucial. A pressure pump is another potential source of grounding issues. Over time, the pump's internal wiring can deteriorate, or the motor windings can develop a short to the pump's metal casing. This can create a path for electricity to leak into the water. Carefully inspect the pump's wiring for any signs of damage, such as frayed insulation or loose connections. Use a multimeter to test for continuity between the pump's metal casing and the ground wire. There should be a low resistance reading, typically less than 1 ohm. A high resistance reading indicates a poor ground connection or a fault within the pump. If the pump is not properly grounded to the electrical panel, ensure that a grounding conductor is connected from the pump's grounding terminal to the grounding busbar in the panel. The grounding conductor should be sized according to the National Electrical Code, NEC Table 250.122, based on the size of the circuit breaker protecting the pump. If the pump is old or shows signs of significant wear and tear, consider replacing it with a new pump that meets current safety standards. Testing this circuit after addressing all potential issues is very important. Before reassembling the system and testing the circuit, it is important to perform a thorough visual inspection of all wiring and connections. Ensure that all connections are tight and secure and that all wires are properly insulated. Use a voltmeter to check for voltage between the water in the tank and a known ground, such as a grounded metal pipe or the grounding busbar in the electrical panel. The voltage reading should be 0. If any voltage is present, there is still a ground fault somewhere in the system, and further troubleshooting is required. Once you are confident that there is no ground fault, reassemble the system and turn on the circuit breaker. Monitor the system closely for any signs of electrical leakage, such as flickering lights or unusual noises from the pump. Use an amp meter to measure the current draw of each pump. The current draw should be within the pump's rated specifications. If the current draw is higher than expected, it could indicate a problem with the pump or the wiring. Consider using GFCI outlets for the pumps to provide additional safety protection. A GFCI outlet is designed to trip quickly, typically within milliseconds, when it detects a ground fault, even if the current leakage is very small. This can significantly reduce the risk of electrical shock. GFCI outlets are readily available at most hardware stores and are relatively easy to install. Ensure that the GFCI outlet is rated for outdoor use and is properly grounded. Test the GFCI outlet monthly to ensure that it is functioning properly. To test the GFCI outlet, press the test button on the outlet. The outlet should trip and the power to the pump should be interrupted. To reset the outlet, press the reset button. Installing a proper ground rod for the holding tank, if one is not already present, can further enhance electrical safety. A ground rod provides a direct path for fault current to flow to ground, which can help to trip the circuit breaker more quickly in the event of a ground fault. The ground rod should be made of copper or copper-clad steel and should be at least 8 feet long. It should be driven into the ground as deeply as possible, preferably in an area where the soil is moist. The ground rod should be connected to the grounding busbar in the electrical panel with a grounding conductor that is sized according to NEC Table 250.122. Ensure that all electrical connections are made securely and in accordance with local electrical codes. Loose or corroded connections can create resistance, which can lead to overheating and electrical fires. Use properly sized wire connectors and ensure that all connections are tight. Protect connections from moisture and corrosion by using weatherproof enclosures or applying a corrosion-resistant coating. Consult with a qualified electrician to ensure that all electrical work is performed in accordance with local electrical codes. Local electrical codes vary from jurisdiction to jurisdiction, and it is important to comply with all applicable requirements. A qualified electrician can also help you to identify and resolve any potential electrical hazards. The presence of copper piping in the residence that is grounded per code provides a degree of safety, as it can help to carry fault current back to the electrical panel. However, it is important to ensure that the grounding system is properly installed and maintained. Check the grounding connections at the water meter, the main electrical panel, and any other points where the copper piping is connected to the grounding system. The connection should be tight and free from corrosion. The size of the grounding conductor should be adequate to carry the maximum fault current that could be expected. The NEC provides guidelines for sizing grounding conductors based on the size of the service entrance conductors. It is important to understand that the absence of grounds in the SJAR codes is a significant safety concern. While the copper piping in the residence may provide some degree of grounding, it is not a substitute for a dedicated grounding conductor in the pump circuit. The grounding conductor provides a low impedance path for fault current to flow back to the electrical panel, which helps to trip the circuit breaker quickly and prevent electrical shock. The fact that the grounds would be sealed up in the bulb floats is also a concern, as it could prevent the grounding system from functioning properly. If the bulb floats are not designed to accommodate a grounding conductor, they should be replaced with floats that are. In addition to the troubleshooting steps outlined above, it is also important to educate yourself and others about the dangers of electricity and water. Never touch electrical equipment with wet hands or while standing in water. Be aware of the signs of electrical leakage, such as tingling sensations, flickering lights, or unusual noises from electrical equipment. If you suspect that there is an electrical problem, disconnect the power and call a qualified electrician. Regular maintenance and inspection of electrical equipment can help to prevent electrical accidents. Inspect cords, plugs, and outlets for damage. Replace any damaged equipment immediately. Keep electrical equipment clean and dry. Do not overload circuits or extension cords. By following these safety precautions, you can significantly reduce the risk of electrical shock and other electrical hazards. Remember, safety should always be your top priority when working with electricity. If you are not comfortable working with electricity, call a qualified electrician. The cost of hiring an electrician is well worth the peace of mind knowing that the work is done safely and correctly. Also, consider a full electrical safety audit of your home, especially in areas prone to moisture. A licensed electrician can identify potential hazards you might miss and recommend solutions to improve overall safety. This audit should include checking the integrity of your grounding system, testing GFCI outlets, and inspecting wiring for wear and tear. Be proactive about electrical safety, and do not wait for a problem to occur before taking action.